So this is problem 7.42 from Griffiths, chapter 7, Introduction to Electrodynamics. So this problem actually really helps you understand how boundary conditions are applied, specifically in electrodynamic scenarios. So it especially deals with boundary conditions in electric fields because we only have electric fields going on around here. But it's good practice of everything from solving Laplace's equation in cylindrical coordinates to, fitting boundaries set again. So we're going to go through the question first, and then we're going to move on to the solution. A rare case in which the electrostatic field E for a circuit can actually be calculated is the following. Imagine an infinitely long cylindrical sheet of uniform resistivity and radius A. So a diagram has been given right here. So this is the sheet that we're looking at. It has a radius A. It is a cylindrical sheet. Inside the sheet, we've got a hollow cylinder basically, and the sheet lining is a metal. So a slot corresponding to a battery is maintained at potential plus or minus V over 2. So what's being talked about are these slots right here. So they're separated by an elementary distance at theta equals plus or minus pi. So if we're going to consider a cross section like this, the positive terminal is an infinite line that's going to be situated at theta. Theta equals pi. Pi approached from the left hand side, and we're going to have a negative potential, negative V naught over 2, maintained at theta equals pi approached from the positive side. So they're separated by a very small distance. Then, so what we've been told is that by Ohm's law, then surface currents are going to be set up along the cylindrical body, because of which a uniform potential gradient exists over this angle, right? And this makes sense if we fit in pi equals negative, um, uh, I'm sorry, if we fit in phi equals negative pi, right? So um, here we've got plus v over 2, and there we've got negative v over 2. I'm exaggerating the distance between them, but um, so that's done more for more for clarity. But then if we fit in um, phi equals pi in this potential, that makes sense. That will give a negative v naught over 2 for phi is negative pi, and v naught over 2 for phi is pi, right? So that makes sense. A negative pi would be us going clockwise, right, in the clockwise direction from this axis with respect to which we're measuring the angle. Okay, so once that's cleared out, once the situation's been cleared out, we now move on to understand what's being asked. So the problem asks us to use separation of variables in cylindrical coordinates, well, we knew that, to determine potential, the solution for potential, inside and outside the cylinder. And we've been given the answers to check whether our final answer matches to this at the end. So let's move forward. So of course we begin by writing Laplace's equation in cylindrical coordinates, right? Um, we begin by writing the uh, divergence of the gradient of the potential is zero equation in cylindrical coordinates, obviously. But then I'm going to present a very short proof for Laplace's equation as well. Some of us might be unfamiliar, or for others, it might be a good revision to get through what Laplace's equation actually is in cylindrical coordinates. So we define the gradient first, right? The gradient is just how much the fields change for unit distances, so how much the field changes along the radial direction, azimuthal direction, and along the height, right, along the z direction in cylindrical coordinates. Once we have that, we want to consider what the divergence of a vector function is. We basically consider fluxes. We basically consider a cylindrical element at a certain given point in the cylindrical coordinates. You can see that. When we consider this cylindrical volume element, we want to consider how much the radius changes. So, for example, this is the small arc, right? The arc that is after a distance, a further distance, radial distance of ds is going to be larger, right? That's the same case with the arcs at the top, right? The front arc is going to be smaller, while the back arc is going to be larger. We want to take the geometry into account, and I think the rest is just apparent, right? The arc length after a distance of ds, this arc length is going to be s plus ds times d phi, right? That's just by the definition of radians. The arc just before that, that is s d phi, and the other geometrical parameters are apparent. We're considering a section of height dz. That's also apparent, and we're considering a radial shift of ds. So that's the element that's being considered. We want to consider the fluxes and the divergence due to due to these fluxes. So the volumes, so the differential volume of the section that's being considered is just s ds dz into d phi. We just multiply length, breadth, and height, right? So length, so obviously one of the lengths is s d phi, the other is dz, and the other is ds. We multiply these three to obtain the volume, and then we obtain the corresponding flux component. So due to the radial field, this is the flux, right? So we consider the flux through the front face and the flux through the back face first, right? We've been considering the flux through the front face and the back face due to the radial components. The same fluxes also exist due to the phi components, the azimuthal components. For example, there'll be field lines that are penetrating through this face and that face, and um, the difference in that will account for azimuthal fluxes, and we'll have vertical fluxes through this because of the difference in the z components of the fields, right? So that's been written. We compute all of that, and all of this simplifies to this neat expression right over here, which will give you the divergence in cylindrical coordinates. Now, what's Laplace's equation? It's basically the divergence of the negative gradient, which is the divergence of the electric field, is zero because it's a charge-free region, right? We're using Gauss's law. We compute what this gradient of the divergence means. We already have the gradient from the first equation, and we already have the equation for the divergence of a vector field, right? So we compute the gradient of the potential, um, and we take the divergence of this gradient of the potential electric field, right? And we set that to zero. That gives us Laplace's equation. Once we have Laplace's equation, we basically see that our solution is of the form that's independent of this variable, independent of the z variable, right? So this direction, the vertical direction, the potential, the solution for potential is independent of where along the height we're choosing it, right? Because it is an infinitely long cylinder. Any height will make no difference to the fact that, uh, any chosen height along the cylindrical axis will make no difference uh, as to the fact that above and below the cylinder goes to infinity, right? So it's the same picture. Everything is independent of height. So we neglect this term that deals with the variation of potential and height, right? Because we're dealing with a certain kind of symmetry at least. Once we have that, we basically need to solve this differential equation, right? And as we do with all sorts of Laplace's equation, we assume a form that has a product solution, right? Where the potential is a product of two functions. One is a function of the radial distance, and one is a function of the azimuthal angle. Once we assume a product form solution, and we can plug this expression into the original Laplace's equation, and we can separate variables as is apparent from this equation. Once we separate variables, we can say that for any value of the radial distance s for this, right, uh, adding this whole function to another function of phi will always give zero. So no matter how we change this, adding a function of phi to this is always going to give zero, meaning that both of them have to be constants, because otherwise that would not be the case, right? The constants that add up to zero. So let this be the positive constant, and there's a reason for this, and let the other be the negative constant. So the issue about the negative constant is going to show up later. Once we say that this is a positive constant, now we can solve for what capital S is in terms of this small s, which is the radial distance. And the solution to that differential equation is surprisingly simple, actually. It's just uh, a random coefficient a, right, which obviously will depend on boundary conditions, times s to the k plus b times s to the negative k. And you can actually plug this solution in into the original differential equation to check if this is valid. And I've actually done that here and proven rigorously that this equation is actually satisfied um, by this solution that we assumed for S, for capital S, right? What we do next is we consider also a solution for what happens when the constant that we assumed, k, is zero. So when k is zero, we're going to have a differential equation of the form um, of this form, where we can neglect both of these because they're just going to go to the other side of the equation and zero out anyway, right? So when that's zero, we can actually solve this equation and find out that there's yet another possible form of solution, which involves the natural logarithm of the radial distance, as you can see, natural log of the radial distance s, right? So that is entirely dependent upon what we choose to be the value of k, or what the value of k is, right? So we're actually missing that solution. So that is yet another possible solution for S, which is for k equals 0. Now we go for capital theta, which we assume to be the function of azimuthal angle only. So this is the uh, form assumed. As you can see in the Laplace's equation that we had, this is what we assumed. So if we set this equal to negative k, or negative k squared, to be more precise, this is what we obtain. Actually, I've actually missed a factor of capital theta in this equation. This is what it's supposed to be because, capital theta goes to the other side. The solution is just the standard simple harmonic oscillator, right? Because we've all seen this differential equation. We've all seen this where the second derivative of a variable is dependent upon negative or constant times the variable itself. The solution to this is a second order harmonic oscillator, right? With conditions determining the value of the amplitudes. Um, so that's that. So that's that. Once we have the solutions for both theta and um, capital theta and capital S, we can actually write the complete solution for potential, the generalized solution for the differential equation in cylindrical coordinates, which happens to be this. Notice that there's the natural log term that we assumed, right? And there's the product of capital S and capital theta, which we assumed the potential to be. Um, Notice that the natural log is separate from any possible solution for capital theta, which we assume to be of this form, and this is because these solutions are only for k is greater than 1, right? K has to be greater than greater than or as big as 1 at least. For the k equals 0 case, we assume the natural log solution. And if we assume k equals 0 for this particular equation, right? Because we're considering the k equals 0 case for capital theta as well, when we do that for capital S, we actually see that we have a differential equation of the form second order derivative of capital theta with respect to phi is 0. And the solution for this is just a constant in terms of phi, right? So when you assume a product, this just becomes a constant times the natural log of S, right? Natural log of S being the solution of the k equals 0 form for capital S. So that's that. This will give you the generalized solution for Laplace's equation in cylindrical coordinates. And now it does not matter what the labels for the constants are, actually, right? Because you might actually see that there's a few algebraic discrepancies between the second last equation and the last equation. Um, because I've factored out sk and done weird things with my constant. But it does not matter what the constants are. Those constants are still going to be determined by um, uh, the boundary values that we're going to fit into this equation, right? So I've factored out sk That means for the cosine term, I'll be left with AK times CK, which are the respective constants for the corresponding value of K, right? So but when I'm writing the final equation, which is equation 3, I've actually said that this is AK because the constants don't really matter. They're still going to be determined uniquely for all possible values of K going from 1 to infinity by fitting in the boundary conditions, right? We're going to fit in those boundary conditions one by one. Right. So we assumed a product form solution, and because we don't know what value of k is going to be the right answer, because all values of the constant k are still going to satisfy this differential equation, right? So one of them is a positive constant and the other is a negative constant. That was the only thing that we assumed. The other is the negative constant. That's the only thing that we assumed. We have product solutions, and since we can use the superposition property of the second order linear differential equations, our solution for potential is basically the superposition of all possible solutions, right? So all possible k's. So k can go from 1 to infinity, and k can basically adopt any possible value, right? K can adopt any possible value, right? And there's no restriction to that. Um, so that was that. It does not matter what the labels for the constants are. So because we're just writing the general form of the solution for Laplace's equation cylindrical coordinates. So that completes the first part of the required analysis. I mean, it's better that you memorize this expression, which is the solution for Laplace's equation cylindrical coordinates. I'm saying this again. But for those that would prefer to go through the derivation instead, you have all the time in the world. I think it's a fair deal to go through the derivation every time you want to, use cylindrical coordinates because it's just nice. Like, why not? Like, let's get things revised. Now we're going to fit in boundary conditions to this equation that we've solved. Okay, so first thing that we can realize in this problem is that when we look at a cross section, there's symmetry in there. So there's a positive potential sign at theta equals pi negative, right? Pi minus of theta I'm sorry, phi approaching pi from the left hand side, and for pi plus when phi approaches from the left hand side, from the clockwise side, it's got a negative, the potential has got the same value but the negative sign. So there should be some sort of symmetry between the solution for potential at this point and at the symmetric mirror point. So this point, right? They should be opposite because that's what our intuition is telling us. It's symmetry, right? Positive and negative. These are the only possible boundary conditions, by the way. These are the only conditions that we've maintained externally. So like things should add up, and symmetry, some sort of symmetry should be maintained, right? So if the solution for potential at this particular point that I've highlighted blue is V, then at the symmetric mirror point that should be negative V. So what that means is that if potential um is an odd function, of phi for the same radial distance s, right? V is an odd function of phi. So when we derive this conclusion, what terms are odd functions here in the generalized solution for Laplace's equations? Obviously, sine terms, right? So we only consider the sine terms. I'm sorry, this is not a cosine term. I made another mistake there. This is a sine term. We only consider the sine terms there because those are the only terms that matter. Okay, since those are the only terms that matter, we move on and consider only the sine terms. So inside, we're going to consider even amongst the two sine terms, one of them has a positive power of the radial distance, and the other has a negative power of the radial distance. So we're going to neglect the negative power because that negative power is going to explode at s equals 0, and s equals 0 is actually a physical point inside, right? We actually plug in s equals 0, and we don't want this term to explode because we plugged in s equals 0, right? We don't want an infinity there, which means that we're only going to consider this solution. And we're also certain that we're not going to have any natural log, any solution that's going to go off as natural log of s, because here as well, if we plug in s equals 0, that's going to come off as undefined because natural log of 0 is that's not something that you want, right? So we're only going to consider this particular solution. And by the property that uh, uh, the potential is an odd function of phi, we also see that at the radial distance 0, as you can see that what I've done there, right? For every phi at the same radial distance, right, even at 0, the potential at a negative phi, that becomes this negative of whatever we considered, right? So that plugging in phi equals 0, this is what we get, meaning that the potential at the center is also 0 by symmetry. Means that this constant term that we've assumed is also going to be 0, meaning we're only going to be left with this particular term, right? So the sign terms with the positive exponents in the radial distance. So this is the only possible expansion for potential, right? Now we fit in boundary conditions at the radius, right? At the radius. So what are the boundary conditions? The boundary condition basically that the potential is defined for along the circumference, right? Potential is defined along the circumference. We use Fourier's trick to determine the coefficients. Obviously, we're going to use this trick that the integral of a function of a sine function, sine of k times phi, um, uh, with a product with a sine of k dash times phi is only going to be non-zero and a constant when um, the second factor considered, k dash, is equal to k, right? That's the only possible thing. So we're going to use this trick, of course. We're going to use this trick, and let's actually determine what this integral is. We're going to evaluate this integral analytically, right? And you can see how I evaluated that analytically because I'm basically using this trigonometric identity, which allows me to separate this in terms of cosines, and that just becomes like really simply integrable. When I fit in the limits pi and negative pi, because that's where I'm integrating from, right? Pi and negative pi, because that's also where the right hand side of my potential is defined for, right? This is the solution for potential when I plug in pi and negative pi, not from 0 to 2 pi, right? When I plug in the limits, I assume that the integral takes this form, right? And when I take the limit for k equals k dash, I assume I obtain that that limit is going to cause me to take this form of a limit, which we're like very familiar with, right? Limit of something which has the form of sine x over x as x approaches 0, that just becomes unity, and that does not vanish to 0, which means that I obtain the integral as a constant, right? And that only happens, by the way, when the second factor of k dash is approaching k, right? Otherwise, if k dash is not approaching k, this just becomes 0. This just becomes k minus k dash just becomes the integer and an integer multiple of pi, and the sign of that is always going to be 0, right? So it's only going to be non-zero when k is approaching k dash, right? We use this trick and determine the solution, right? So what we've essentially done here is, so imagine that we have a, actually, let me actually rewrite what I've done. Let me actually rewrite Fourier's trick for all of you, those of you who are unfamiliar with it. So this sum is basically going to be a to the first power times b1 times sine to the 1 phi plus a to the second power times the second coefficient times sine to the 2 phi plus, we're going to have all of these terms here, and let's say we've reached the ith term, so we're going to have a to the ith exponent, a being the radius of course, times the ith coefficient times sine of I phi, right? And that's going to be the RHS. So we're going to integrate all of this with a certain sine to the I phi d phi, and we're going to integrate that from negative pi to positive pi. And from what we know, we can distribute this to all of the terms. And from what we know, all of these terms, when I is not 1, I is not 2, I is not 3, I is just I. Only this term is going to survive after the integral. So meaning, if only that term is going to survive, we can actually, and the right hand side, and in the right hand side, we've got something of this sort, VFI 2 pi integrated with, of course, the same factor, right? After this is evaluated, we're only going to have this particular term left in the left-hand side, meaning that we can determine what the ith coefficient b subscript I is, right? So that's Fourier's trick for you. I've demonstrated it actually with the expansion for those of you who are unfamiliar with it. Once we have that, we can actually determine the kth coefficient, right? As I said, once we have this integral in place. So the second integral also I've evaluated analytically. Those of you who are interested in the mathematics of this integral can go through this. But this integral basically comes out to be negative 2 pi over k and negative 1 to the power of k, right? So we basically have this sort of a solution for um, the kth coefficient in the expansion for potential inside. And once we fit in the coefficient, but that's all that we really wanted, right? This becomes the solution, right? In fact, let me just circle out the final form. This becomes the uh, this becomes the solution inside, right? And outside the fitting at the boundaries, the potentials, right? Fitting the potentials at the boundaries, because outside we're gonna have a form of solution which is going to be this, right? Outside, have I written the form outside yet? Or have I just discussed the inside form yet? So inside, of course, this is going to be the form of the solution, and outside, of course, outside, this is exactly going to be the form of the solution that's not going to be present. Outside, only s, the negative exponents of s are going to be present, because outside, if these exponents are present, then s approaching infinity is going to explode these terms, right? Of course, the cosine term does not even exist, only the sine terms exist, but positive powers of the radial distance are going to explode these terms. So only these terms exist, and only this particular solution exists, right? Only these particular terms exist outside. And when we equate the outside potential with the inside potential at the boundary, at the periphery, because the solution for potential has to be continuous, we obtain that subsequent potentials, I'm sorry, subsequent coefficients for the outside solution are related to the subsequent potentials for the inside solution, right? So outside, this is the form of the solution that we assumed outside. When we plug that in terms of B, we get this, right? And since B, B we already know is this, we can also obtain the solution outside. And all we use for this is just continuity, right? So that's about it. That's about it, actually. We've obtained successfully, and we've actually successfully solved the problem right here. We've obtained the solution for potential outside of the cylinder, right? By continuity after having determined the solution inside, right? And we did that by using Fourier's trick in order to determine individual coefficients, right? And we evaluated some numerical integrals. All we did was fit the boundary because we knew that the boundary condition for potential is just given by this expression, right? That was given in the problem statement itself. So that is all we did. We just fit the solution into Laplace's equation um, and used some sense. But there's something more to do. And what's more to do is that this particular form for solution outside, this sum is actually evaluatable in a closed form, right? So we basically have a sum of this form if you want to compare, right? Where x is for the outside case it's negative a over s, right? Or for the inside actually, for the inside that same x is negative s over a, right? So if we compare the inside solution and the outside solution, it's just is it either s over a or a over s inside that bracket, right? But then we have a sum of this form in the potential, basically. The thing is that mathematically, if we use some mathematics and some Euler expansions and some Taylor theorems, we can actually evaluate this in a closed form, and which is what you saw in the problem statement. In the problem statement, we saw that the answer was obtained in terms of a very analytically evaluatable function, not in terms of an infinite sum, right? So we've got a tan inverse function there. So how do we get to the inverse tangent from a um, how do we get to the inverse tangent from um, a solution which has an infinite sum in it, right? So the issue is that this sum has to be expressed in a closed form, for which we're going to use Euler's theorem, right? Euler's theorem for a complex number written in polar form and broken down into real and imaginary components. So, because we have a sine of k phi here, we can use this term to say that sine of k phi is just the imaginary component of the Euler's e to the I k phi, right? Written in polar form. That's just the imaginary component. You can get that expression. We can plug the imaginary function out if this thing is the if the sum has basically the imaginary components. We're taking the product with imaginary components. We can just as well take the imaginary component of the whole sum, right, together with it, right? And since we're both raising negative x and e to the I phi to the power of k, we can basically write it like this, right? We can take the imaginary function outside and we can use the property of exponents, right? Once we have that, we say let's try expanding this sum actually, and let's see if it resembles anything. And it turns out it actually resembles um, this expression because we know the expansion for the natural logarithm function, right? We know the expansion for the natural logarithm function. Natural log of 1 plus y, any constant y, that's just y minus y squared over 2 plus y cubed over 3 minus y to the fourth over 4. And that's also the form that we obtain here, meaning that this has to be natural log of 1 plus whatever quantity that we're interested with, right? Once we have that, we can pull out the negative sign, right? We can pull out the negative sign because imaginary component of a negative complex number is still going to be negative of that imaginary component. Negative sign can still be pulled out, right? Now we consider what it means to take the imaginary component of a natural logarithm of a complex number, whereas of a complex number, z is any complex number, right? So let's say that we are actually doing that, right? Let's say we're actually doing that, right? We're taking the imaginary component of the natural logarithm of some complex number, and that by natural logarithm's property is just going to be this, right? And when we're taking the imaginary component of this particular complex number, we can see that this is the real part, and this is an imaginary part. Theta is an imaginary part, right? So obviously that's going to give you theta. So whenever you're taking the imaginary component of natural log of a complex number, you're basically getting that theta. Theta, by the way, that's just when you represent a complex number in polar form, that's just that angle that it makes with the real axis, right? So you're gonna have the imaginary component there, you're gonna have the real component there. Theta is just the angle that that vector is going to make in the real and imaginary plane, right? Real imaginary Cartesian plane. Um, so theta is just that angle, is that argument angle. And how do you get theta? Of course, uh, theta is going to be the inverse tangent of the imaginary component by real component, right? So when you say that you're taking the imaginary component, the natural log of this function, you're basically taking theta, theta being the inverse tangent of the imaginary component over the real component. We can use Euler's expansion again to write the imaginary and real components, and we get the inverse tangent function like that. So inside, of course, x was s over a. So we replace x by s over a and we get a solution of this form. And outside, we had a solution of the form negative a over s, right? So outside that same component, x, outside, this was x was a over s. And replacing that, we obtain a solution uh, of this form. And the only difference inside and outside is that um, S over A is replaced by A over S for the outside solution, right? We obtain the infinite sum in a closed form, and that's about it. So this was what we had to obtain. As for the second part of the solution, we're asked to find the surface charge density, and that's pretty easy actually, right? So what's the surface charge density at the surface of the cylinder? Once we have the solution for potential inside and outside, we can obviously use the fact that the radial component of the electric fields are going to be obviously the negative gradients, right? Negative gradient outside, negative gradient inside, and their difference is going to be equal to the surface charge density at where you've evaluated the distance over the permittivity of free space. This is just standard Gauss law result, right? We differentiate the individual terms, we use chain rule, and after a long, tedious algebra, we obtain the surface charge density. So the second part, that's not very physically complicated, right? The mathematics is not complicated, it's just a bit bashy, and you don't want to be mistaken anywhere in the algebra. But the second part is not that physically tedious. It's just algebraically a bit tedious. So we've also obtained the surface charge density at the surface of the cylinder. So all we did in this problem was we fit boundary conditions. We fit boundary conditions, and for the surface charges, we evaluated the difference in the radial fields by having evaluated the potential in a closed form. So it was the mathematics that got us from an infinite sum form solution to a closed form, which was actually possible to traverse from an infinite sum to a closed form. How did we obtain to the closed form in the first place? Well, we basically fit boundaries. We basically said that the potential at the potentials inside and outside, those solutions have to be continuous at the boundaries, right? And for the inside part, we basically said that uh, because we already know what the potential at the boundary is, we can basically determine the coefficients one by one by applying Fourier's trick, right? Fourier's trick. And how did we get to a position where we could actually, single out the coefficients, meaning that we knew what coefficients to use, right? We knew if it was just this part to use, or it was just this part, or it was just this part or this part to use. Well, we did that by checking symmetries. We did that by saying that, potential has to be an odd function. So obviously we're going to neglect the cosine terms, and inside we're going to have to neglect the negative power of the radial distances because obviously they're going to explode, and outside we're going to have to neglect the positive powers because outside they're going to explode at infinity. And we neglected the right things, and we got to this position for the inside potential, right? We used Fourier's trick to determine the coefficients, and that is how we solved the problem. So you can note the final answers for the problems. So the solution for potential inside and outside, it's given by these expressions right here, right? And the solution for the surface charge density is given by these expressions right here. And you can check with the original problem statement where they've given the final answer key if this indeed is the correct solution. Thank you.